Rainfall intensity is used to compare the validity of the indices. However, the area of bars in the hyetograph revert back to the rainfall depth. Learn more here in hydrology. For a certain water basin, if precipitation occurs, there are water losses and possible runoff if the rain is ample enough. In order to compute for the runoff, we need to make the infiltration constant. This is done in three methods. The first is the phi index, with the concept that the rainfall volume is equal to the runoff volume. The second is the F average method, taking the average infiltration loss throughout the storm duration. The third is W index, which takes the infiltration rate during the time the intensity is more than the infiltration capacity rate. The W index is another method, very similar with the phi index. This method takes into account the initial losses in solving for the infiltration. Mathematically, W index is the precipitation less the runoff and the initial losses, all over the duration of the rainfall excess. That is W is equal to P minus R minus I sub A all over T. This equation is just like the phi index, only with initial losses subtracted. Graphically, this is subtracted from the first entry. Just like the phi index, there are possibly multiple iterations when looking for the W index, as the procedure is also by trial and error. Every step from the phi index is also observed for the W index, with just an additional step of incorporating the initial loss in the equation. The second example contains a record of rainfall depth of a storm over a watershed with 50 square kilometers area. There is an initial obstruction estimated to be 6 millimeters, and the direct runoff volume is also measured as 1.2 million cubic meters. We are to determine the W index in millimeters per hour. The rainfall intensity is used as the parameter to compare the validity of the index, so we compute for it. But first, add a column for the pulses. Rainfall intensity, though, is the incremental depth over the incremental time. So check the provided time column. What are recorded are the cumulative values. Then compute for the incremental time. For the first entry, 1.5 less 0 is 1.5. Next is the gap between 1.5 to 2, which is 0.5. The third entry is 1.5 hours from 2 to 3.5. The next is 4 minus 3.5, which is 0.5. Then the last entry is from 4 to 6 hours, which is 2 hours interval. Now check the provided rainfall depth. The values rise and fall, which means this is a column for the incremental depth. This would show that we can compute for the rainfall intensity. The first entry of 6 is taken from 9 divided by 1.5. Then 6 divided by 0.5 is 12. 20 over 1.5 is 13.33. Next is 10 upon 0.5, which is 20. And 5 divided by 2 is 2.5. Now we have the rainfall intensity. The next thing to do is to take the area of each bar in the hyetograph. But to save time, we only work with the table. We are not to plot the graph anymore. The area of hyetograph is the precipitation or rainfall. This is the incremental time times the rainfall intensity. So we have 1.5 times 6 as 9, then 0.5 times 12 as 6. Next is 1.5 times 13.33 as 20. Then 0.5 by 20 is 10. Then 2 times 2.5 is 5. Take a closer look at the values. They are the same as the provided values under rainfall. Getting to know that revelation, move on and work on W index, which only differs from the phi index by taking off the initial abstraction from the first entry. In this case, the initial abstraction is 6 millimeters. So the precipitation for W index has to change a little bit, and that is with the initial entry of 9 minus the initial abstraction of 6 giving 3. All the remaining rainfall stay the same, 6, 20, 10, and 5. Having completed all the necessary parameters, we can take the first trial of solving W index. The first trial considers all the 5 pulses, covering 6 hours. The function is P less Wt is equal to R. P is the summation of the precipitation, where we get 44 millimeters. R is given in the premise as 1.2 million cubic meters. Divide this by the area of the catchment, which is 50 square kilometers. Convert the area by multiplying the conversion of 1,000 meters for a kilometer. So R becomes 0.024 meter. Convert this again into millimeters by multiplying the conversion factor of 1,000 millimeters per meter. R is then computed as 24 millimeters. The function then is 44 less 6W as equal to 24. Then the W index is 44 less 24 all over 6, simplified as 3.33 millimeters per hour. This value of W is higher than the last rainfall intensity of 2.5, which means there is a next iteration. The next trial is to take out the pulse lower than the previous index. This trial considers the remaining 4 pulses, and the time duration is 4 hours. Using the same function, take the summation of precipitation, which turns to be 39 millimeters. Plug this in the equation and have 39 minus 4W as equal to 24. The W index is then 39 less 24 all upon 4. This gives 3.75. Checking on the rainfall intensities, the W index is lower, meaning there are runoffs for the 4 pulses. So W is 3.75 millimeters per hour.